we want to graph function y equals 2x cubed plus 15x squared plus 3x plus 9. To graph it, we're first going to just take the information we can get from the first and second derivative. So first calculate those derivatives and then see how we can use that information. By now you should know that the first and second derivatives give us a lot of good information about a graph. So first derivative, the derivatives are obvious. Derivative of 2x cubed, derivative of x cubed is 3x squared. Multiply that by 2, you get 6x squared, etc. Very straightforward to take these derivatives, just a polynomial series of simple power functions. Now, I claim that the derivative, or the graph, is level, okay, and by level I mean has a horizontal tangent line. Here's an example of a graph. This is not the graph of this function, but here's a typical graph behavior. And the graph is level anytime the function hits a maximum or a minimum. And it can also be level at a point like this, where it's coming up like so and levels off for an instant and then goes back up. So that's another possibility. So just because a graph is level doesn't mean it has a maximum or a minimum. We could have this behavior as well. Okay, so again, graph is level means the tangent line is level, slope of the tangent line is 0, and the slope of a graph at a point is the value of its derivative. So the derivative is 0. Okay, so the graph is level when y prime equals 0. So we set y prime equal to 0. Here's our expression for y prime. We set it equal to 0, and we solve it. Now, this is easily solved. We get x equals -2 or x equals -3. And we call these our critical points, the points on the graph actually, but the x values can also be regarded as critical. So the critical value of x is -2, critical value of x could be -3, meaning that the graph is going to be level. One of these types of behavior is going to occur at each of these points. So we look at the points one at a time. Okay. Now I make the statement here, if there's a relative max or relative minimum, then it has to be at one of these points. Another important thing to understand is these are the only points at which the graph is going to be level. These are the only critical points. These are the only points at which the first derivative is 0, and if the first derivative isn't 0, then you're not going to have any of these behaviors. Okay, so a relative maximum is going to occur if the graph is level, i.e. if you have a critical point, and the first derivative goes from positive to negative. Okay, so here's a maximum point. What's happening? First derivative is positive on one side, negative on the other side. That constitutes a maximum. Alternatively, it's level, again, critical point, horizontal tangent line, and the second derivative is negative, meaning that the graph is concave down. Okay, second derivative negative means that the graph, for example, in this case, has positive slope, less positive slope, less positive slope, 0 slope, negative slope, more negative. Okay, so the slopes are decreasing. Slopes on this side are decreasing towards 0. Slopes on this side are decreasing past 0, at least up to a point here where the concavity changes. So a maximum occurs when you have a critical point, so the graph is level, and the graph is concave down as indicated by a negative second derivative. Okay, now again, a negative second derivative means the first derivative is decreasing. Okay, second derivative is the rate of change of the first derivative. So decreasing first derivative gives you this behavior. Okay, a minimum occurs if the graph is level or critical point or horizontal tangent line, and the first derivative goes from negative to positive, as it does here. First derivative is negative, hits the 0 point or the level point, the 0 of the second of the first derivative, and then comes back up. Okay, so the first derivative in that case goes from negative on one side to positive on the other. First derivative, as we know, indicating the slope of the graph. Okay, alternatively, level, second derivative is positive. Second derivative positive means the graph is concave up. Why is that? It's because the first derivative is going from negative to positive. Okay, we could say that. If the first derivative goes from negative to positive, then it appears that the first derivative is increasing, and that is the case here. Large negative, lesser negative, negative approaching zero, slopes negative approaching zero, slopes then becoming positive and increasing. So second derivative is positive, graph is concave up, you have this relative minimum. Okay, well then, at x equals -2, one of our critical points, the derivative is 0, and the second derivative, easily evaluated, we plug in -2, we get -24 plus 30 equals 6. Graph is concave up, meaning that there's a minimum at x equals -2, relative minimum, and I should be using the word relative here, relative minimum at x equals 2, and that then occurs when x equals -2, we plug in -2 for the x, and we get the value of y to be -19. And I believe that's right. I had a question mark there. At x equals -3, we do the same thing, but this time when we evaluate the derivative, we get -6. So when we evaluate the second derivative, we get -6. And we see then that the graph is concave down. I couldn't read my own writing there. That's not very well written. But it's concave down at x equals -3, which means that there's a relative maximum at x equals -3. And if we get the coordinates of the -3 point by plugging -3 in for x up here, we get y equals -18, giving us this picture. Okay, we have a graph that hits -18 as a relative max at x equals -3, and then hitting -19 as a relative minimum at x equals -2. So let's just now the scale of this graph is exaggerated between here and here. Okay, this point won't look all that much lower on the graph than this point, but I wanted to be sure to show clearly that we have a relative maximum here and a relative minimum here.